So let me first of all start with brief introductions. For those of you who don't know me, I'm Jarka Glassey, and I'm current Vice President Executive of EFCE. I'm actually a professor of chemical engineering at Newcastle University, as you can probably see at the background behind me. I don't know whether it shows sort of a mirror image for you as well, but that's just to tax the brain in the morning for those of us that are in the Northern Hemisphere. As I mentioned, I work at Newcastle University and I'm a biochemical engineer. So for me, drying is actually a really important area of our research, although I concentrate mainly on modeling and big data and process development, but still drying area is absolutely essential for a lot of the work that we do as well. And it is my pleasure to do this very short introduction, first around the EFCE and around the spotlight talks, and then just hand over to our chair today, Angelique Leonard, who is our chair of the Working Party on Drying and who will take you through the rest of the program today. So let me just say a few words about the EFCE Spotlight webinars. This is actually the third year now that we are running them, and we've introduced them in 2020 for very obvious reasons. When the pandemic hit, this was the only way we thought we will be able to keep the community at least meeting virtually and exchanging ideas. The success of these spotlight webinars was such that it convinced us in the management group of EFCE to carry on, and we are running this as a third series and indeed planning to keep running 2 sets of webinars each year as long as we can. There are today, this week, there will be, and the next week, there will be 8 of such webinars on various topics organized by our technical groups, that's working parties and sections, and drying has the privilege of starting off this 2-week set of webinars. So I'm sure you'll all enjoy that. And the idea behind these webinars is basically to provide fellow experts and people interested in issues surrounding chemical engineering with an opportunity to discuss matters that they may not have been able to attend in person, or might have actually enjoyed just listening to something slightly different and cross-fertilized between different specialist areas. We are recording these webinars, as you've seen the notification, and the recordings will be available on the EFCE website and also on the EFCE YouTube channel, and you'll get more information on this on the EFCE website. Since I mentioned EFCE, just to say a few words about it in case you didn't know, EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, which brings together something like 100,000 chemical engineers across Europe. And really, the beating heart of EFCE are its working parties and sections which deal with all the technical aspects of chemical engineering and provide a really important forum for technical exchange and networking amongst chemical engineers in Europe. And I would really like to thank everybody in those working parties and sections and in EFCE in general for making these spotlight talks happen and making them work this effectively. But I think the greatest thanks go to Martine Poux, who is also with us in the call, who works with us in EFCE. She's actually in Toulouse, and she's the person who made it all happen. So all the conceptual setting up and practical work, it's all down to Martine. So thank you very much. And as I said, I'll keep this very short, so I'll stop here and I'll hand over to Angelique, who will hopefully make sure that your webinar today is very fruitful and successful. And I wish you all the success for the future. Thank you.
So thank you, Jarka, for this kind introduction. So it's up to me. So my name is Ange. Some of you knows already me. So I'm full professor at University of Liège. So it's in the French-speaking part, so that you can recognize my accent of Belgium. And so I'm also the head of the chemical engineering research unit in this university. And I, let's say, the pleasure to chair this working party on drying. So I have just a couple of slides to share to make this introduction. So here they are. So as it was already said, it's a pleasure also to introduce this first, let's say, webinar about among the 8 that are organized under the umbrella of the EFCE. So let's say that we start this week with you. So thank you for, let's say, being part of this webinar. For the, let's say, the program of today, so about drying, we will have 3 different talks, so you can, let's say, see the faces of the young researchers that will share their work. So I'm also, let's say, very, how to say it, active in, let's say, gender balances in the research. So I'm also very happy to see, let's say, young females presenting their work today. And I have also, you know, the period of the, let's say, the last 2 or 3 years were not so easy for, let's say, communicating and disseminating research and participating to, let's say, live events. And so I really the pleasure to announce you the dates of the next year drying conference. So it will take place in Poland, in, let's say, in Łódź University. So our colleague from, let's say, Poland will welcome us, let's say, in July next year. So you can have some, let's say, pictures about the venue. So in Łódź city, which is a city with, let's say, 4 different cultures, with, let's say, a lot of different nice things to visit, let's say, besides the scientific program. Or, let's say, the scientific stuff will take place at Łódź University of Technology, where there is a real strong chemical engineering department with a strong activities, let's say, since years related to drying. And they have, let's say, a beautiful facilities where we will have the opportunity, I hope, to exchange in real life. So it will be a real pleasure to meet a lot of you there, yes, next year. So the website is, let's say, about to be released. So you will see it through different channels. And so with, let's say, the mailing list that we have, let's say, from, let's say, a previous editions of this year drawing or even IDS conferences. So we hope to have you on board. I would like also to say at the level of the EFCE Drying Working Party that, let's say, all the countries members of EFCEs are not represented. So we are missing some delegates from some countries. So if you are interested to join, let's say, the group at the level of the Working Party of Drying, don't hesitate to send me a short email. We still miss some, let's say, delegates from industry, but also from academia. So don't hesitate, let's say, to let's say, send your application. It will be a pleasure to, let's say, welcome you on board. And it's also a possibility to participate to some scientific committees, to propose some events related to drying. And of course, we just want to continue to make growing this drying community and to, let's say, continue to make these fruitful exchanges as it's the goal of today. So I will not be, let's say, more, or I will not be longer than that. So I will really I wish you a good webinar. And so I will, let's say, let the floor to our first panelist of today, which is Julia Veser from Wageningen University, so from the Netherlands. So Julia, it's up to you. And don't hesitate to use the chat if you want to ask some questions after, for, let's say, the discussion after the presentation. So thank you and enjoy this morning.
Yeah, thank you very much. Good morning. I'm just sharing my screen. I hope it works. Takes a bit of time. Yeah, now it should work. All right. Then, yeah, good morning, everybody. And thank you very much for this opportunity to have a talk here. To start off this presentation, I would like to start with a short quiz question for you. So my question is to you, why are seeds important? Because they are the basis of life, more worth than gold, of economic importance for the Netherlands. Just think about it yourself, answer it for yourself. I give you some seconds. yeah, it can be either 1, 2, or 3, or there are also several answers possible. What do you think? Actually, it's all 3. So seeds are, of course, the basis of life. We all know that for plants, but that also means for feed for the animal, and therefore also for majority of our food. They are also more worth than gold. So certain seeds, for example, tomato seeds can be per gram to be more worth than gold. So they have a higher price per gram than gold. And they are of economic importance for the Netherlands quite a lot, because if you look at the numbers, Netherlands exports around 1 million tons of seeds, vegetable seeds, every year. And if you compare it to the second largest, USA, it's only 0.5 million tons. So really, Netherlands has a big importance in this field. And yeah, it's quite important for the Netherlands. And I think this importance of seeds is a bit lost, this knowledge, in various fields of the society in the Western culture. However, in African cultures, in developing countries, this is still quite aware, people are still aware of that, because for them, it's really the basis of life. They need to have good seeds for the next season to have a good harvest. So in this picture, you see African women picking seeds for the next season, and that's a very important task, so that you have healthy plants for the next season, which give a good yield and therefore a good harvest and a good food for you. Of course, in our culture, still the farmers know a lot about the importance of high quality seeds. So they also want to have high quality seeds that can withstand all difficult situations from environment, that are healthy and that give a good yield, so that they can sell, in this case, good cabbage and good vegetables. So these farmers, they often go to companies like Rijkswaan or Bio, seeds companies that sell high quality seeds. And for these companies, of course, they want to ensure high quality. And how do they do that? So yeah, here you see cabbage seeds growing to the cabbage we can consume then and we can buy. And they want to really ensure high quality. Therefore, they treat the seeds. So they harvest seeds and they treat them in between. For example, they wash them, they sort them, and they prehydrate them, so that we can ensure a good germination and good and healthy plants. However, these treatments, often they are wet treatments, you need to dry them. So we come back to the drying part. And this drying still can affect the quality of the seeds. On the other hand, also, if you then want to really slowly dry and give that it doesn't affect the seed at all, then you need a lot of energy to dry that. So until now, these drying protocols are quite standard, and you'd really try to dry the seeds quite gentle and slowly. But yeah, it's not really well known how does the drying affect seeds, and how could we change the drying that we dry more efficiently. So therefore, we in our project really want to investigate this drying of vegetable seeds. We want to model this drying. We want to understand what is happening within the seed, how is it affecting the quality in the end. We will perform drying trials in our lab and connect it to quality, which in our case is germination quality. Yeah, with that short introduction, I'm coming to our talk today. It's called Towards Efficient Drying of High Quality Vegetable Seeds. I'm Julia Veser. I'm a PhD candidate at the Wageningen University in the Netherlands at the Food Process Engineering Group. And together with my supervisors, Martin Schruttheiser and Ruud van der Smaan, and also the seed companies Rijkswaan and Bio, we work on this topic. And is this seen? No. Yeah, and my topic where I'm working on now since 1 year is actually called Efficient Fluidized Bed Drying of High Quality Seeds. And here you see a nice overview from the whole seed process, from flowering plants, the seed production towards the final plants and cabbage, which can be sold. And my project focuses on these seed treatments. First, we will look into single seed drying, building a model, understanding the drying of seeds and connecting it to seed quality. And later on, we focus on fluidized bed drying and optimization of the drying. For our talk today, I will focus on the fascinating seeds. I would like to give you a short introduction, as I think it's a quite new topic for many of you. And then I want to focus on our model, how we approach the modeling of seed drying, and end with a short outlook towards efficiency, how we will tackle this. Let's start. I gave you already a short introduction to the seeds, and here you see the seeds a bit more closely. So on this side, we see the cabbage seeds, and we see some lettuce seeds, where you see really a very different shapes, which is quite fascinating, I think. And if they are really close up now, so usually they are around 2 millimeters. I brought you some here. So you see they're really tiny seeds. These are the cabbage seeds. And what I think that's very fascinating, they look so dry and dead, like little stones actually, but they have a lot of life inside. So here you see a cut seed, and you can look into the inside and you see the little embryo of the plant. And these points here, these bit darker tissues here are basically the cotyledons, so the first leaves that will be formed. And we see here the radicle, the first root, which will be formed. And if you give a little bit of water to these seeds, yeah, the life comes alive and a little plant comes out of it, which is quite fascinating for me. The typical cycle of the plants starts with a flowering plant. These flowers, there the seeds are getting produced. So we have a little seed where we inside have this embryo with the cotyledons and radicle, as said. And the seed then, if you give them a bit of water and the right conditions, develops again a seedling, which goes to the flowering plant. I want to introduce you to one more topic of the seed science, which is called priming. And I can explain it quite well with this graph. So you see on this axis water content over time. And if we first look at the blue line, we see how the water content changes while we give some water to the seed. So first it's imbibing, it increases, then it stays constant. So then we have the metabolism activation phase, where actually the energy metabolism starts, DNA repair, cell cycle activation. So here the seed really prepares to get alive, to grow. And then at a certain moment, the water content increases again, and the radicle comes out. So we call that germination. And yeah, the plant grows. For the priming treatment now, we start this whole process. We look at the green line. We start the whole process with imbibing, and we go into the metabolism phase. But then just before the germination happens, we dry back. So here comes in place the drying where I'm looking at. And why do we dry back? We want to dry back so that we can increase storage, that we can sell the seed later to the farmer, and that later on we can have it on the field. And the big advantage of this is that the final germination then on the farmer's field is much quicker. So if you look at this curve, the first two phases are much quicker because they started already. So the seed is already prepared. And yeah, on the field, we have a quicker germination and also more uniform. That is also proven. I tested that with some of my seeds. You see a germination test, and they start to germinate, and then they germinate further. And if you compare now on this graph, the percentage of germinated seed over time, in green the fresh ones, and so directly dry from the mother plant, and in orange the primed ones, which were prehydrated and dried back again, you see that the orange line is quicker and a bit more uniform. The big drawback of that whole priming treatment is that storage is a bit less than if you have the seed directly from mother plant, because of course the seed is already prepared already, so it's a bit less, it's more vulnerable than before. All right, so that's some background of the seeds, and let's take a look now into the dehydration step, how we are going to describe that with a model. Therefore, I provide you with our approach, which we have in this kind of model circle, where we always start with the system analysis. So we really want to know, okay, what is our system, how we are going to translate that system into a model, which are the important parts, what are the important assumptions. Then, of course, we need some input parameter. We can measure characteristics of our system, like diffusion coefficients, radii. Then we can build our model and predict, in our case, the drying curve, evaluate that with a certain drying experiment in our lab, and of course then go back to the cycle and improve what we want to improve, that the model describes the data better. And we go through the cycle until we're happy with our model. So let's start with the system analysis. For that, we look at cabbage, and we assume that we have a sphere with two layers with certain characteristics like the radii, diffusion coefficients, and we want to look at drying, so basically taking up the heat, increasing of temperature, and water diffusing out of the seed and evaporating at the surface. So our model is based on basic heat and mass transfer equations. As assumptions, as input first, we have the dry weight and the radius and constants, and of course the drying air with the temperature, velocity, and relative humidity of the air. And as output, we are interested in the moisture content over time, the temperature, and the radius of the seed over time. Yeah, the assumptions we base this model on are first spherical geometry of our cabbage, that we have two materials, embryo and coat, that we have a uniform temperature within the whole seed, and that the quality depends on moisture and temperature. And as boundary conditions, which we always need to solve our equations, so the conditions in the boundaries of time and also in the boundaries of space means, so in the initial time, we think that the temperature and moisture content of the seed are uniform. And in the spatial boundaries, so inside the seed, we assume that there's no water influx, or all the water goes from inside to outside. And at the surface of the seed, the diffusive flux is same as the evaporative flux. With this, we can build our model. And I directly jump to our model. And therefore, I would like to introduce you to the core of our model, the simple diffusion model. And I brought you a very nice scheme from, it's built with Visual Grind by MATLAB. It's a very nice software to visualize what is happening inside a model. And if we only focus on this diffusive part of the model, we see here a slice of the seed with the embryo inside and the coat. And the model makes different shells or different slices of our seed from inside to outside. This is depicted with these different blue boxes. And then per time step, we calculate how the water moves basically from one shell to the other shell. And that we do for several time steps. And so it's an iterative process. And for each movement of the water, this movement from one shell to the other is described with the basic flux equation of diffusive flux, where we have constants like the diffusivity constant, the thickness of the layer, the area of the layer, and of course the driving force, the concentration difference between two different shells. So that's the basis of the model. And with very also taking out some concepts like we don't have shrinkage included, we only have a constant diffusivity, not dependent on water content. We have a constant heat transfer. We obtain these results. In blue, you see the modeling results describing in the orange experimental results of water content over time. And we are quite close, so that's quite good already. If we now include all these other concepts, so we include shrinkage, so the area gets smaller while we dry, we don't have a constant diffusivity, depends on the moisture content of the seed, and we don't have a constant heat transfer, then we obtain these modeling results. We see the radius decrease over time and the normal total weight over time. Another question is, of course, how is the model performing now? And before I show you that, I would like to introduce you to our evaluation methods. Let's see how can we evaluate our model. And therefore, we quickly take a look into the companies. We also, we got some ideas from them how to perform that best in our lab. And here you see some drying equipment. One typical drying is the seeds drying in hot air. And the other thing would be here a typical fluidized bed dryer. For us, I worked together with my master student, Iris Sasseler. We first developed a priming or the hydration method, and therefore we use drum priming. That means we add a certain amount of water and a certain amount of seeds in these little tubes, and then they are turned slowly for some days until the seeds are really fully imbibed and started this second phase of metabolism activation, but have not germinated yet. For the drying, we use this thin film dryer. It is originally used for polymer films that are dried on this little plate and observed for the drying. But for us, it works very well. We can add our seeds on this little plate, and this plate is connected to a scale so that we obtain this really nice drying curve over time of our seeds. In principle, this lid is closed, and we have a nice airflow distribution over the seeds, so the seeds can dry in a hot air stream. And we want to have also controlled conditions for the drying. Therefore, we added a humidifier where we have, on the one hand, a water flow and a dry airflow, which get connected and mixed, evaporated in this evaporator of bronchos. And then we have a controlled moist and heated air with the temperature and relative humidity we want to have. So in total, this is our system, how it looks like, where we have the humidifier on the one side connecting to our thin film dryer, where we can observe the weight of the seeds and also the temperature with an infrared camera. how the temperature of the seed evolves. We have one step further where we would like to investigate or to evaluate and to measure how is the moisture content within the seed, inside the seed. And therefore, we would like to use the MRI, magnetic resonance imaging. And together with Julia Krug, an assistant professor at Bionanotechnology at the University of Wageningen, we did some pre-trials which were quite promising. So first, a quick introduction. What is magnetic resonance imaging? Here you see quite a big machine in Nijmegen here in the Netherlands. And basically, you put your sample inside a magnetic field. This magnetic field gives a certain pulse to your sample, and protons inside your sample react to this pulse. So basically, you detect the signal of protons. And yeah, as water has a lot of protons, you can kind of say if you detect this, how many protons are there, you know how much water is there. You can also detect the how different populations of protons, if the water is more bound or less bound. For us, for our samples, the first pre-trials look like that. So what do we see? First, we see fresh seeds, so basically dry seeds directly from the mother plant. Then we have hydrated seeds, and then dried seeds after the hydration. For the first one, we see a quite evenly distributed signal. So all the white spots indicate protons, and the whiter it is, it means the more protons are there. In our case, we assume it is water. However, oil also has a lot of protons and gives also a signal. And in our cabbage seeds, we have quite a lot of oil, around 30%. So we assume that in this dry seed, we mainly have oil, which we see here. In the hydrated one, we of course expect also water. And there's a phenomenon happening here. You see a black line on this side, but not on the other side. So that indicates a chemical shift in the signal, which is an error because we have protons from two different materials. So we have this oil-water difference, which we see here, indicating that we really see also water. Probably this white line, which should go all around, indicates water. And also in these pores in between, we probably see water. And for the dried ones, we see again, quite evenly distributed signals, so basically mainly oil. But what's also very interesting here, that we see quite big gaps in between, which indicates air. So that was quite interesting to see for us that actually we have quite a big air gaps inside the dried seeds. All right, so these are all the methods we want to use to validate our model. Let's have a look how the model performed. Perhaps that as a quick outlook also, we would like to transform these MRI images then into these different, in these color maps, let's say, that is from Lee et al. Another literature, to see how the water content from blue to red evolves over time. So that's the aim, what we want to perform. But first have a look at our basic model. And here we see now for the first graph, the radius decrease over time, then the weight decrease over time, and the residuals from the weight. And in colorful colors, we see the experimental results. So in orange, the radius decrease we measured, and in green, the weight decrease we measured. And what we see, the model performs very well for the radius decrease, however, not very well for the weight decrease. So we had a look at our diffusivity constants, which we also model. And you see the black squares is the model of our diffusivity constant over moisture content. And in blue, we have our measured diffusivity constant, indicating that it doesn't fit very well. So we try to improve that by fitting an equation to our diffusivity constant. And if we look at the model, it kind of improves because we go into a better range for the weight decrease. However, we of course then don't describe the radius decrease very well. This also actually indicates that they are very linked together, these two decreases, but it's not really describing the reality. And basically we need to go now to an improvement step. So we are in the last box of our circle, and we can think of how can we improve it. As said, these are, if we change the one side, we also change the other, and it doesn't really improve. So therefore, we need to decouple these two. And one thought is about shrinkage. At the moment, we assume ideal shrinkage. So basically, the water that evaporates of the seed, that's the volume that is also lost. So that's the volume how the seed shrinks. So that's the connection between the weight and the radius shrinkage. So, however, we don't have this connection. And if we look at this graph where we see the volume shrinkage of seeds over time, we have in green the ideal one, so basically the weight-based shrinkage. So that indicates the volume that is lost because of the water that is lost. That's the volume we should also see that decreases. However, if you look at the radius data, so the real shrinkage we see that the shrinkage is much less. And so that's indicating this non-ideal shrinkage, which is not included in the model yet. And actually, we could also see this non-ideal shrinkage in our MRI images. And yeah, here depicted graphically, at a certain moment, probably the radius, the overall radius doesn't shrink anymore or less. And inside, we have like, yeah, a development of air pores. And here, again, our MRI images where we clearly saw this phenomenon happening. Also on top, you see some microscopy images where we make thin slices of the seeds. First, we have the hydrated one and then the dried ones, where we really also see these air pockets evolving. So that's a point where we can improve our model and where we are at the moment working on that. And yeah, I think it's quite promising. We will mainly improve the model and hopefully soon have a good model describing the drying kinetics of seed drying correctly. Yeah, with this, I want to come to the last point towards efficiency. How are we going to include this efficiency optimization? For now, we have this general idea of a state diagram. So we would like to produce a state diagram for seeds where we have the temperature of seeds and moisture contents of seeds on the axis. And we have quality constraints curves in between, because that's the biggest goal. We want to keep the high quality of the seeds. We don't want to lose high quality due to drying. And therefore, we would like to include germination. Of course, that's the biggest quality constraint and quality characteristic. How well and how fast do the seeds germinate? And on the other hand, we have this glass transition curve that is perhaps not very clear at the first moment. It actually indicates the optimal storage conditions. So the endpoint, where do we want to reach after the drying? Because if we have a glassy state of the seed, so the cytoplasm of the seed get in a glassy state, all the oxidative processes or biochemical reactions that can happen and deteriorate the seeds will be slowed down and kind of stopped. So we have a longer storage possibility. So that would be desired. So with this kind of diagram, which we are going to build the next years, we think and we hope that we can then evaluate different drying paths, how to reach this optimal storage conditions, and how to do that within the quality constraints without damaging the seed, but still going to the limits perhaps to have a more efficient drying. Yeah, so that's the outlook for the next years of research or next months of research. And with this, I'm at the end of my talk. I hope you got a nice overview of perhaps a new field for you, the plant science, the seed science, how we are going to model the seed drying and how we're going to optimize it towards efficiency. And yeah, I would like to say thank you for your attention. And also, I hope you always keep in mind how important seeds are.
Okay, thank you, Julia, for your nice presentation. Coupling, let's say, at the same time, experimental, let's say, testing, advanced characterization tools, but also modeling. So let's say very complete work, I would say. So I don't see any question in the Q&A, but I have some questions for you. As your picture shows, so at the end, you saw that some voids appear at the end of drying, or at least during the course of drying. You said at the end of the presentation that at the end you would like, let's say, to optimize the drying path in order to, let's say, optimize the storage condition and so on. Have you still, or have you already an idea about the impact of drying conditions on the extent of these voids creating on these cracks?
Yeah, definitely. So in this case, we see one extreme drying, which is with a quite low drying air. So basically a high driving force where we have nearly 0% or like 4% relative humidity. So that's quite a harsh drying, I would say. Therefore, we have this quite big gaps. And until now, we couldn't evaluate more drying pathways in the MRI, but I assume that if we do that with a higher relative humidity, perhaps a bit longer, then we won't have this big cracks. So I definitely think that we can vary that with different conditions.
Okay, and is it possible to relate, let's say, for example, a further germination characteristics to these voids, or is it good or not for future use of the seeds? I'm not an expert, so it's a stupid question.
No, it's not a stupid question. That's actually one of our research questions, or questions we want to follow. Definitely, we want to find out if there is a relation. So that's one of our next steps. As the project started, we are not that far in this regard, but that's definitely an important question. I think that there might be definitely a relation, because if you try too hard, the cell may break and they are not really healthy anymore, or you have, they are just not, not intact anymore as before. And if you do it more slowly, they can more slowly adapt to it, and they will have a better germination in the end, or will be quicker because they don't need to repair that much before they can germinate.
Okay, and concerning your model, do you consider that internally it's homogeneous concerning internal diffusion, or is it, let's say, the same coefficient everywhere, or is it, let's say, or is it depending on the location inside the seed?
Yeah, so for the first basic model, we assumed it's constant everywhere. We only have this distinguishment between the inside and the outside, because we have a thin coat around the seed, and that's quite a different tissue than the inside embryo. So there we make a distinguishment between the two diffusion properties also. But within the whole embryo inside, at the moment, we assume it to be constant. And we hope that, with including this porosity or this air layer development in the model, we can describe the data already good enough. But of course, that would be a next step to say, okay, there are different tissue layers. Perhaps we need to take that also into account.
Okay. You also mentioned that, let's say, the shrinkage cannot be considered as ideal in your case. Would it be an option or not for you to include some also mechanical modelization, or to couple mechanical aspects to the mass transfer and heat transfer? Or is it out of the scope?
No, very good that you mentioned that. We actually looked into that as well. Indeed, if the mechanical properties can indicate when we change from ideal to non-ideal shrinkage, and we are considering it. However, what we found for now, that if you look at the glass transition stage, that also is already good indication, so that we can, if we reach a glassy state in the coat layer, that then we kind of have a certain hardening and we kind of stop. So that's a kind of condition we can use already, which is kind of also mechanical indication, that then we have a change in shrinkage. So definitely that's relevant.
Okay, so last question before going to the second presentation. Of course, in your work, you focus on, let's say, a cabbage, but from, let's say, studies in your group or from your knowledge, the, let's say, intrinsic characteristic of the seeds are very different from one plant to another. Let's say the order of magnitude, for example, of internal diffusion can be very, very different, or the seeds are quite, let's say, in the same range, or?
Yeah, so far we focus on cabbage, and we will go on later to lattice also.
Okay.
And I don't have a lot of data yet, but so far I think it's quite similar. So the material is quite similar, let's say, from the inside. What the big difference is the coat. So for cabbage, we only have a thin coat. For the lattice, we have actually two coats, whereas the outer coat is much more woody. You could also see it in the image. We had really this woody structure around it. So that might influence it quite a lot, or will influence it quite a lot, because that's a bit bigger protection also of the seed, and also then for water diffusion.
Okay, so thank you a lot for your nice presentation.
Thank you very much for all the questions, and for all the attention. Thank you.
Okay, so now I invite Tibor from Budapest University of Technology to share his presentation. Yes, sorry, but Julia, there was a small question that I didn't see. I will just ask this before, let's say, starting with Tibor. So are you considering diffusion coefficient to be dependent on temperature?
Actually, we also do that, yes. So for the when we fitted it to the measurements we had, there we didn't. We only had it on moisture content, but the original model is also taking temperature into account. Yeah.
Okay, thank you. Yeah. So Tibor, it's up to you. So we'll listening to a presentation about dimensioning of drum dryers. and let's say a review of the design parameters. So from Hungary, as I said, Budapest, so nice city. So the floor is yours.
Okay, thank you, Chair. Joining to Julia's research topic, I would like to show you another methods for drying seeds near the fluidized bed drying. So I would like to welcome the audience. My name is Tibor from Hungary, and the topic of my presentation is the operational dimensioning of drum dryers and review of the design parameters. In my presentation, I will describe the main types of drum dryers and their heat and mass transfer models. I will present the drum dryer in our laboratory. In addition to the drying measurements, the mixing power requirements were also measured. In this picture, you can see an industrial rotary drum dryer for biomass examined via another project, but it's easier to imagine how this machine looks like. Based on the literature review, I describe the main geometric parameters of the rotary drum dryers. Finally, I will show you what other measuring equipments are available in our laboratory, mainly used for drying research. I divided the presentation into 3 underlying topics: heat and mass transfer, mixing, and construction parameters. According to their design, 2 main types can be distinguished: agitated drum dryer and rotary drum dryer. The agitated drum dryer is suitable for drying materials which are less prone to fragmentation. The central element of this dryer is the horizontally positioned drum and the mixer inside, designed according to the technology. The mixing elements rotates continuously during the drying process. The mixing elements don't transport the material to axial direction in batch operation. Their function is only to mix the material and create a contact surface with the drying gas as large as possible. The hot air drying gas enters one side of the drum and transfers its heat to the material in the drying chamber, absorbing the moisture and leaving it on the other side of the drum. The drying gas may carry dusty material separated by a cyclone and or air filter after leaving the dryer. The rotary drum dryer has a cylindrical drum, which is the central part of this machine, and it's made of steel, and its axis has a slope of approximately 1 to 5 degrees. The materials enters at the top of the drum and leaves at the bottom. The flow direction between the material and the drying gas can be either co-current or counter-current. The drum wall can be fitted with flights of different shapes and numbers and sizes, thus modifying the contact surface between the material and the gas. The flights leave the particles, and at a given height, these particles fall out like a curtain. Most of the drying occurs in this falling period because there is the best contact between the material and the gas. In these drums, 3 operations can occur together or separately. Mechanical mixing is the first. Mechanical mixing is often used for mixing ingredients in granules or coating the granular materials, like in pharmaceutical industries. During mixing, the state of the particle motion depends mainly on the drum's rotational speed. 6 different states of motion can be distinguished depending on the rotational speed. This can include slipping, slumping, rolling, cascading, cataracting, and centrifuging above a critical rotational speed. Rolling and cascading are the most suitable for drying. Another operation is the heat transfer. In this case, only heat is transferred or removed from the material. For example, during soil disinfection or heat treatment of food. In this case, conduction heat transfer through the wall is often used. If the heat transfer is followed by evaporation, we are talking about drying. The equipment is mainly used for drying particulate materials, including agricultural seeds. For example, Julia's presentation contains pharmaceutical particles, fertilizer granules, biomass like sawdust, and centrifuged sewage sludge, and so on. In the following, I will describe the main knowledge about drying when using drum dryers. Mathematical models can describe the drying process. The purpose of this model is to determine the changing of the drying characteristic. Depending on the continuous or batch operation, the drying parameters can be written as a function of drum length or the drying time. We examine the drying characteristics are the moisture content, the temperature of the material, and the humidity and the temperature of the drying gas. The models make it possible to investigate the effect of the properties on the drying characteristics. For example, how the drum loading factor, the specific heat of material, its density, or its desorption, isotherm properties affect the drum geometry or the drying time. Miklestad was one of the first researchers who described with equation how the moisture content of the material change along the length of the drum in a countercurrent convective rotary drum dryer. Researchers always validated the calculation results with measurements as shown with points in this figure. One of the biggest problems in the dryers is determining the contact surface between the drying gas and the particle. Since calculating the surface only gives good results under certain assumptions, treating it as one factor with the heat transfer coefficient, the following correlation can interpret the volumetric heat transfer coefficient. The calculation of the actual surface area of the drying particles and the surface of the heat and mass transfer due to the irregular geometry and the size distribution of the material and the irregular contact between the material and the drying gas causes great uncertainty. As the particles move, they clump together and crash with each other or with the device walls. Due to this kind of disorder, the surface of the particle is not equal with the heat and mass transfer surface. Thus, the volumetric interfacial surface area depends on the drying and mixing method, the size of the equipment, and the physical properties of the particles. The volumetric heat transfer coefficient can be interpreted for different cases. It can be gas to particle, wall to particle, and gas to wall, and these are indexed accordingly. The value of the volumetric heat transfer coefficient can be determined empirically. Many equations for determining this volumetric heat transfer coefficient between gas and material for a rotary drum dryer are available in the literature. The following authors has created the most commonly used correlations. The best known of these is Miklestad's equation, derived from measured results, where the volumetric heat transfer coefficient is a function of the mass flow of gas per the cross-section area. This correlation is still used in a computational algorithm today. The volumetric heat transfer coefficients found in the literature have only been established for gas particle case and are only applicable for rotary drum dryers. To determine the coefficients for agitated drum dryers, a measuring station and the measuring method was created. In this figure, you can see the semi-industrial size batch agitated drum dryer located in our department's laboratory. The agitated drum dryer has a U-form drying chamber covered by a flat plate. The feed is agitated by an electric motor. The drying gas flowed axially on the left side and let out at the other end at the top. The cylindrical bottom part of the dryer has a controlled electric heated jacket here. The construction of the dryer makes it possible to carry out experiments with either conductive or convective heating or by applying both. The dryer with the electric engine is built on a frame on the top of a scale to measure the mass change during the drying. The humidity of the drying gas entering and leaving the dryer is measured using a capacitive humidity sensor. Differential pressure on orific flow meter is measured by transmitter to determine the mass flow rate of the drying gas. Thermocouples were used to measure the inlet, outlet, inlet and exit air, wall temperature, orific temperature, and atmospheric temperature. An infrared sensor in the middle of the dryer is used to measure the surface temperature of the particles. The drying air was heated by an electric heater with a maximum capacity of 12 kilowatts. The drying air temperature was controlled, which is a maximum of 120 degrees of Celsius. The dryer wall was heated by an electric heater with a maximum capacity of 4 kilowatts. The maximum wall temperature is 90 degrees of Celsius. And then the measured, all of the measured parameters were recorded every 10 seconds using an Almemo type data logger. Measurements were performed at different drying gas temperature, wall surface temperature, gas mass flow rates, drum loading factors, and rotational speeds of the agitator. The results are plotted on a graphs. As an example, I will show the results of sunflower seeds drying. The figure on the left shows the drying gas inlet temperature at the top, under the drying gas outlet temperature, the heated wall surface temperature with green, and the surface temperature of the particle with red as a function of time. The diagram on the right shows the change in mass of the material. The evaluation was carried out for the section with a constant drying rate period. If conductive and convective drying was investigated, I determined from the measured values not only the gas particle, then the wall particle, and wall to gas too. With these values, I calculated the volumetric heat transfer coefficients using the following equations, whose members are the temperature difference, driving force between the gas particle and the wall particle, and the drum volume, and so on. From the measured results, first I calculated the volumetric heat transfer coefficients. I used them to generate a modified dimensionless number, where I used the volumetric heat transfer coefficients instead of the normal heat transfer coefficient. To make this correlation dimensionless, I have squared the characteristic diameter. The effect of the drum or mixer rotation was taken into account by the resultant vector of the velocities. The resultant can be calculated by the circumferential velocity determined from the rotational speed and the axial velocity of the drying gas. Using this resultant velocity, a modified Reynolds number can be calculated, which now considers the rotational speed of the drum or the agitator. The ratio of the modified Nusselt number to the Prandtl number between gas particle is plotted as a function of the modified Reynolds number. Two different cases were considered. The X-shaped points were referred to values measured during conductive-convective heat transfer, while the circle-shaped points refer to values measured during only convective heat transfer at drying. I observed that the points plotted in a logarithmic scale coordinate system are aligned to a good approximation of a straight line. The equation for these shown here. Since the two lines are nearly parallel, transforming the two equations of the fitted lines with the correction terms. The equation can be used over the specified modified Reynolds number range at the specified drum loading factor, and the ratio of the temperature can be seen here in this slide. Next, I will show you the results related to the mixing of particles when using the agitated drum dryer. Mixing power requirements measurements were performed on the agitated drum dryer, which was shown. The electrical power consumed by the mixing motor was measured by a special three-phase power meter at the 1 second sampling rate and recorded by a computer. The measurement was started by filling the air-dry bulk material into the drum, in which the mixing power requirement was examined at different loading factors between 10 and 25% in 5 steps. The total volume of the drum is about 47 cubic decimeter. The rotational speed of the mixer can be changed with a frequency changer between half and 1.6 revolutions per second. The electric power consumed was measured in the meantime. From this value, the no-load power consumption had to be deducted. In order to determine this no-load power consumption, no-load power measurements were carried out at each rotational speed without particles. So the real mixing power consumption can be determined from the measured power consumption minus the no-load power consumption. Some results of the laboratory measurements are shown in these figures, where the real mixing power is depicted as a function of the rotational speed for various drum loading factors. Based on the results, it can be established that the mixing power requirements increased as the drum loading factor of the drum was increased because the mixing elements move more material. And the last project topic in this presentation is the mainly used design parameters of drum dryers in the research. The convectional rotary drum dryer dimensions, design data, and operating parameters were collected used in the research. The main construction parameter of the dryer is the diameter, the length of the drum, the slope of the drum, the type and number of the flights, and the rotational speed of the drum. The following data on the various rotary drum dryers used in the research are presented in this table. In addition, the geometric dimensions mentioned above include the material and drying gas flow direction, the method of material loading and removing, and inlet drying gas temperature and velocity in the drum. The results of several other research are included in our original bigger table, but only the parameters of convectional dryers without wall heating have been copied here, and only those works that provided sufficient information for the required data. The data described in this table shows that ratios, characteristic values, and narrower data ranges can be determined. One of the main characteristic ratio of drum dryers is the Z per D ratio, which is the drum length and the diameter ratio. It can be observed that for smaller devices, this ratio can be between 6 and 8, while for the industrial devices, it can be higher, about 15 or 20. The rotational speed doesn't always show the mixing behavior for rotary drum dryers. It depends even more on the diameter of the drum. Furthermore, it's advisable to compare the rotational speed to a limit at which the material hasn't yet started rotating with the drum, because centrifugation would occur. The following equation can calculate this critical angular velocity value. The ratio of the actual angular velocity and the critical angular velocity can be determined, which is about 0.1. The velocity of the drying gas is mainly determined by the particles density, size, and drag coefficient. So depending on the material, the value of the velocity varied in a wide range between 0.1 to 6-7 meters per second. And in the last slides, I would like to show you some devices in the drying topic which can be found in our laboratory. We have got 6 different dryer types in our laboratory at Budapest University of Technology and Economics. The first is the drying chamber. You can see its picture here. We have a vacuum drying chamber. There is in our laboratory a convectional, or other named hot air dryer, and the agitated drum dryer, as already mentioned. You can see a video during the agitating process. Next is the fluidized bed dryer. You see the feed and the withdrawal of the particle left side and the fluidization process in the drying space right side. The sludging stage of fluidization can be observed well. And the last one is the spray dryer during a measurement. We dried in this examination protein in this case. So here is the drying chamber. Here you can see the cyclone. We separate the dust and air. Here is the initial product which will be dried, and it's on a scale. So we can measure the mass flow rate of the dry product during the measurement. Furthermore, I would like to show some devices which can be used to determine the parameters of the dried material and which are used in the preparations for the drying measurements. The first is the wind, or other name is air classifier. We can use this machine for dust separation and select particles with nearly the same parameters, diameters. The maximum drying gas velocity, which is below the value of pneumatic transport velocity too, and we can determine in this wind classifier. And the next is the air pycnometer, which is used to determine the bulk and the particle density and the porosity of the bulk. We use vibratory sieve shaker to determine the mean diameter of the particles. This is usually the characteristic length in the dimensionless numbers. An important drying parameter of the material is the desorption or adsorption isotherm, which can be determined with this gravimetric sorption isotherm device. This drying chamber has already been shown in the presentation. We use this to determine the moisture content of the particles. And in this video, you can see a rotary drum mixer used to wet the particles before the drying examination, but also we can use this machine to determine the dynamic angle of repose for DEM simulations. And we have already made examinations to determine the mixing index of the mixing process. And finally, I would like to introduce the member of the drying research group at our university. I have 2 PhD students, Evelyn and Daniel. Evelyn's research topic is the open surface liquid evaporation, and Daniel's topic is the particle mixing in the agitated drum dryer with the aim of DEM simulation. My colleague Cornel is an expert in DEM simulation. Maria was my supervisor during my PhD work. And finally, Victor is my graduated PhD student whose topic is the fluidized bed drying. And I'm the head of this research group. This research group has a website. We will regularly upload the new results to this website in the near future. And finally, thank you for the members of the working parties that they were given me an opportunity to introduce my research group and its topics. And thank you for the attention of the audience.
Thank you for the presentation. So we have 5 minutes left for questions. So there were some questions from Martin in the chat. So the first one concerning your equipment, is the air humidity controlled in your equipment?
No, the air humidity is not controlled. We use ambient air for drying, but in the near future, we use the control air because the convectional drying, the hot air dryer was uploaded with nozzles which flows some waters and mix to the air. So I hope in the near future, in some months, we can control the humidity. But this control is only increase the humidity of the air, of the drying air. So we couldn't decrease it.
So another question also from Martin. The good mixing of the product is a big advantage of the drum dryer, but the bad heat transfer from air to the product is a big disadvantage. Therefore, we sometimes prefer belt dryers with airflow through the product for a better heat transfer. Are there other advantages than the good mixing for drum dryers?
Mm-hmm. So belt dryer, yes. I think the heat transfer is. I haven't had any examination, and I haven't used belt dryer before, and I haven't got any experiences of it. But I think in the mixer or in a rotary drum dryer, there are a very good mixture between the drying gas and the dry product. But I haven't compared these two methods before, so I couldn't answer this question well. So I hope I show you some dryer measurements in our laboratory, but we have no belt dryer, so I haven't got any experience for it.
Okay, so the question from
but the rotary drum dryer and the agitated drum dryer is used for example, seaweed sludge. And I think seaweed sludge we couldn't dry it on belt dryer. So for some particles and for some materials, I think the properties of the material is better, the drum dryer.
Yes, but I can tell you that in a lot of, let's say, wastewater treatment plants, belt dryers are used also for sludge, so it's not the same.
Yeah.
So another question from Alberto Di Renzo. Can you give us an indication on typical drying times for a given material in your units?
How can I? Sorry, I don't understand. How can I measure drying times or what?
Yes, no. Could you give some estimation of a typical drying times? Is it minutes, hours?
It's hours. The duration of our drying process is about 1, 2, or 3 hours, and we dried only 1 bucket, so 10, 15 kilograms seeds during this measurement. So it's a very slow process. So that's why we couldn't make so many measurements what we like. But thanks for the students, university students, we always make some measurements every semester, but we can make only 10 or 20 measurements in one semester because of the duration of this drying process. And you have to know that this 10 or 20 measurements is only the valid or the good measurements. So what we can use in our research. So we have made some bad measurements because the preparation of the material is not well, or there are some instrumentation problem on the equipments. So I think the success measurements is about 20 per semester.
Okay, and so a question from Victor Aguirre. Scaling up unit operations that include mixing can be cumbersome. Are these equations that you showed valid for very different equipment sizes? So what about the scale-up issues?
Yes, we hope. That's why we use or we make this research to can scale up our results to an industrial size dryer. and I showed you only some laboratory measurements, but you have to know that we made some simulations. I make some slides about the simulation results, but I didn't know that I have time or not to show it for you. So if you have 1 minute, I try to show it to the audience. So can I share this?
Yes, 1 minute, of course.
And again, now it's shared. I don't see. So you can see my slides.
Yes.
Yes. Okay. So here on the right side, oh, sorry, I closed this window. So in the slide, on the right side of the slide, you can see the comparison of the real and the simulated videos. The first phase of the simulation involved particle bulk generation by considering the drum loading factor. In the next step, the gravity deposition of the bulk was commenced, and this mixing was performed for half minutes, so 30 seconds at each rotational speed, and the torque impact the shaft was sampled at each second, and the mixing power requirements can be calculated based on the torque and the rotational speed, and this simulated power requirements can compare with the real one. So we haven't made any comparison between the industrial and laboratory research results, but we have made some comparisons between the simulation and the laboratory results.
Okay, so last question, which programs do you use or softwares for the simulations?
Yes, we used in the before slide, you can see we used the Jarka software for it because it's open source, so it's free for the students.
Okay, and very last question before, let's say, going to the last presentation. In the first talk from Julia, she also worked on seats, but let's say not at the same level, and she focused also on the quality and using MRI techniques to see, let's say, or to have an insight about, let's say, quality of the product. Do you also try to monitor the quality of the product depending on the, let's say, on the type of drying that you apply to the seats?
Yes, we haven't examined the quality of the seats, so it's a problem of our research that we haven't got any techniques or machine to examine these parameters. We check only the diameter of the particles, how does it vary during the drying, and we measure the moisture content before and after the drying. So the shape of and the geometry of the particles hasn't been examining.
Okay. Yes, so perhaps there is place for a collaboration with, let's say, a faculty of agronomy, something like that. Perhaps in your yes.
Yes, we hope. So we are medical engineering, so we would like to cooperate with Julia too. Yes.
Okay. So thank you for this presentation and for all the questions in the chat. So now we will move to let's say presentation number 3. So I will ask Supriya Bhaskaran from Otto-von-Guericke-Universita of Magdeburg in Germany to share her screen. And so she will talk about Lattice, Boltzmann, and Pore network models, which is, let's say, a strong field of research of this group. So it's up to you.
Thank you. Thank you for the introduction. So today I would be talking on the topic of multiphase flow inside the anodic porous transport layer of PEM water electrolyzer, based on 2 different models, that is the Lattice, Boltzmann, and the Pore network models. So this is actually totally different from the other 2 topics where I had my team members who spoke about drying, but now I would be focusing on the PEM water electrolyzer. So before getting into the topic, I would give a brief introduction about myself. I am Supriya Bhaskaran. I have 2 of my other PhD colleagues, that is Harshir Altaf and Tamara Milik. We all 3 of us are working under the Max Planck Institute in collaboration with the Otto-von-Guericke-University. And we are like 1 year away from our PhDs. And we are working under the supervision of Tanya Vidakovic, Evangelos Sotsis, and also Nicole Forhauer. So to know more about and what are the facilities that is available at our university as well as the institute. So at the university, we have a very interesting 3D imaging facility, that is the MicroCT, where we can reconstruct our porous structure to a resolution of maximum resolution of around 2 micrometers. And we also deal with the Pore network and Lattice Boltzmann models, where we in detail study the mass and heat transfer in the porous materials. And at the Max Planck Institute, we have the dynamic model for electrochemical processes, where we deal with the macro scale fuel cells and electrolyzers. And also we do the experimental analysis, where we have the validation of developed multiphase models. So to know more about our research group, you can also look into the website. I would try to put the website in the chat as well. Yeah, so today I would be mainly focusing about the motivation and why we have to study the PEM water electrolyzer and why is it important. And then I would be discussing how we extract the porous structure from the MicroCT. Later on, I would give a brief description about the 2 different models that we are working on, the Lattice Boltzmann method and the Pore network model. Later, how do we combine or compare these different models that we have? And later, how can we extract the parameters to our macro model? And later, as you all know, for all the models, there needs to be some experimental validation. So I would also show a prototype about how we experimentally validate our models. So starting with why water electrolysis. So as you all know, we are moving, there is a lot of consumption of energy in the current state, and we have to reduce somehow the carbon emission. So everyone is moving towards a clean fuel source, which is hydrogen. So for this, one of the major contributions is from the water electrolyzer. So the basic parts of the water electrolyzer are, we have the anode side and the cathode side, and it is being sandwiched between the catalyst coated membrane. So in the anode side, we have the flow channel and the porous transport layer and the anode catalyst. And then we have the membrane, and then the cathode side, again, we have the cathode catalyst, then we have the porous transport layer and the flow channel for the cathode side. So for the electrochemical process inside the water electrolyzer, we need to supply electricity. So for this, we get the electricity supplied from the renewable resources that is available. That's mainly from the solar energy and the wind energy. So with this electricity supplied and the entry of water to the anode side, we have the electrochemical splitting of water occurring at the anode catalyst layer. And then we have the splitting to hydrogen and oxygen. Oxygen moves to the anode side, and we have the hydrogen moving towards the cathode side. And this hydrogen is later used to fuel the automobiles as well as fuel to the industries. So this porous transport layer would be our main focus, because it is a very tiny structure which is used to send the water, flow the water from the flow channel to the catalyst layer, and also a pathway for the removal of oxygen. So the main thing that we deal here is the titanium felt porous transport layer. And this is an image that we obtained from our MicroCT. So the major motivation here would be to see the operation at high current densities and significant voltage losses. And the main problem here is the limiting mass transport through the porous transport. So how do we determine this mass transport? So here we mainly focus upon our experimental and our multi-scale modeling approaches. So why anode porous transport layer in main? Because this anode porous transport layer as a complex process. So we have the flow of water supplied to the catalyst layer, and then we also have the removal of oxygen. So this countercurrent two-phase flow that is occurring in this porous transport layer makes it more complex, and also gives a mass transport resistance to the flow of water as well as the oxygen. So this automatically affects the overall efficiency of the anode transport and the reaction process. So with this idea about the anode porous transport layer, we would be dealing this problem at 3 levels. That is starting from the micro scale, then we move to the mesoscale and to the macro scale. So at the micro scale, we apply the Lattice-Boltzmann model to know the invasion physics at the pore scale. And then we move to a bigger size of the porous. We consider a bigger size of the porous structure where we deal with the pore network model. And again, we see the invasion pattern of oxygen as well as water. And also we extract the parameters to the macro scale model. So in the macro scale, we consider the entire system. So we get an overall idea about the efficiency once we modify this anodic porous transport layer. So now, before getting into the models, we have to extract the data of this porous structure. So how do we do this? So in our group, currently, we are working on this commercially available titanium felt, which is provided by Tech Germany. So, and then we scan this using our in-house X-ray tomography at a resolution of around 3.9 micrometer. So this resolution basically depends upon the sample size. So for the best resolution that we could get was around 3.9 micrometer. And the thickness of the material was around 0.85 mm. And the overall porosity of the material is around 80%. So once we get the image data about the structure, we go to the reconstruction of the pore scale. So here, first we apply the binarization step where we have the white and the black space. So these whites are the solids and the black space is the void space or the pore space. So once we define the two phases, that is the pore space and solid, we have to know more about the pore space dynamics or the pore space dimensions. So for this, we use the watershed transform where we use different markers to identify this pore spaces. So once we identify this pore spaces based on different markers, we inscribe a sphere and we try to get the sphere diameter and consider this equivalent to the pore diameter. So once we get the pore diameters, we then evaluate how many number of pores we have for each diameter and how this distribution is occurring across the porous structure. So once we have this idea, then we move to our different models, that is the Lattice-Boltzmann and the pore network model. So what is Lattice-Boltzmann model? So Lattice-Boltzmann model is a alternative CFD tool, which is more recently used by many researchers in different fields to study the single phase and multi-phase flows in porous structures. And it accommodates the real scale pore geometry for multi-phase studies. And it also acts as an solver. And we also use the Lattice-Boltzmann model to upscale it to our network, to other scales, that is the pore network model or to macroscopic models. So I would give you a brief description about how we consider the Lattice-Boltzmann model. So here I have shown a two-dimensional structural view or a cross-section of the anode porous transport layer. So the black denotes the solids and the white is the pore space. And then we assume a catalyst layer from which we have only one active site from which the oxygen is evolved. So we have here the flow of oxygen and also we have the flow of water at the in the counter direction. And with this, these solids and the pore spaces are divided into multiple lattice nodes. So each lattice nodes approximately has in 2D 9 different distributions. So with this help of distributions, we have our Lattice-Boltzmann equation for multi-scale. So this distribution basically is a function of distance as well as time. So once we calculate these particle distributions for each lattice node, and then we sum these distributions, we get the density value as well as the momentum description. So this is a simple explanation in 2D, but in 3D, we have 3 different directions, that is the X, Y, and Z direction. So we have to have another direction. So in total, we have 19 directions in 3D, but this can also be increased to 27 or even decreased to 15. This depends upon the numerical stability and other factors about the model and for which application we are applying. So this is the general description about the lattice Boltzmann model. And then we move to the Pore network model. So here we have the Pore network model, which we represent the porous media as pores and throats. And it's a pore scale approach, which is very efficient at lower capillary numbers. And this model deals with the Young's Laplace equation, where we calculate the liquid pressures. And this is less computationally intensive than the lattice Boltzmann model. And also we can extract the parameters to our macro model. So now I would explain how we extract these pores and throats. So here we have our fibrous network, and we first differentiate between our solids and void spaces. So once we have this void spaces, we mark those voids and the connections between the two pores via the throats. So, and then we consider our pores and the throats. So this is a simple idealized network, but how in real it looks something like this, where we get the exact pores and throats connected in an irregular network. And then we assume a catalyst layer side at the bottom, and then we have a flow channel at the top side. And we have the invasion from the catalyst side to the flow channel. So now how we compare our LBM and PNM in 2D. So here I have considered 3 different PTL structures, that is the felt, foam and sintered PTL. These as approximately 68, 77 and 57 porosities respectively, and a mean pore diameter of 33, 62 and 23, and also a throat diameter of 22, 45 and 77. As I said before, that LBM can actually incorporate the real geometry. You can see from the experiment, we could actually derive the exact geometry and apply our lattice Boltzmann model. And we also got a similar invasion trend of oxygen comparing the experiment and LBM. Whereas in PNM, it was more of an idealized network where we simplified the experimental structure to a network of pores and throats. And then the reduced model based on the liquid pressures were applied. Whereas in LBM, you can also see that we could, in ice, see the tracking of how the oxygen and differentiate between the water and the oxygen. So this makes it more computationally more effortful than what we see in the Pore network model. So this is how we do it in 2D. And then in 3D, we use the irregular network of PNM, and we have our LBM simulation for the same commercially available felt. But here we have considered a smaller cross section because it's computationally more effort and it needs a lot of time to run the simulation. So for the purpose, we have right now considered a smaller cross section of the porous transport layer with approximate porosity of 61, the pore diameter of 58, and the throat diameter of 35. As you can see here, the oxygen saturation across the height of the PTL, we could see a similar trend for both PNM as well as LBM. But there is a magnitude difference between the PNM and LBM. This is due to the inefficient derivation of the pores and throats that we derive from our porous structure. So a lot of focus right now is to how we can modify this pore throat volumes in PNM so that we could match this difference in the saturation values and the pore volumes. So this also depends upon how we modify the Young's Laplace equation by including a shape factor, which is our future goal or our main focus right now. So once we get the saturation values and the pressure data across the Pore network model, we then use the Huygens-Poiseuille equation to calculate the mass rate. So once we get this mass rate, then we calculate the absolute and relative permeability across the model. So this is more important to know how the invasion occurs or how much amount of water is retained in the system. So the more amount of water we have in the system, the more the further reaction of oxygen or hydrogen takes place, and there is no blockage in the system for the water to flow from the flow channel to the catalyst layer. So the major data that we would require is the permeability and the pore invasion pressures. So once we derive this Pore network. Once we derive this data from the Pore network, we move to the macroscopic scale. So in the macroscopic scale, again, for the anode layer, we use the continuum model equation, where we take into consideration our reaction terms, the spatial dependent porosity, the absolute permeability and relative permeability, as well as the capillary pressure for each pore into our nonlinear model. So this is under development right now, and it would be nice if we are able to get more efficient, more of the data about the efficiency, the potential of the electrolyzer. So this is one of our scope that we are right now working on the macroscopic model. So as I said at the starting, that all these models requires a experimental validation. So for this purpose, we have a microfluidic device, which is made from a PMMA material. So here is the schematic representation of our experimental setup. So our major focus, since it's on the anode side of the porous anode side, so we have made the anode porous transport layer as a homogeneous distribution of pores and throats. And the cathode, since it's not the major focus, we have just kept it blank. And between the anode and the cathode, we have the CCM coated membrane. So we have the membrane coated with the anode catalyst as well as the cathode catalyst. And as a current collector, we have used a platinum mesh, so which transfers the electrons, and the reaction occurs at the catalyst layer. And then we see the one-by-one comparison of the invasion pattern once we start the process, and how we can also study how the variation of water flow rate and current density occurs. So before me showing about the video, I would say what you can actually see in the video. So you can see this transparent part, which would be the oxygen generated from the catalyst layer. And you also can see how the water, which is moving towards the flow and removing the oxygen out of the porous transport layer. Yeah, so here you can see how the reaction occurs at the catalyst layer, and we could see the oxygen bubble moving towards the porous transport layer. So once it reaches through the end or near to the flow channel, we could observe the removal of this oxygen bubble and again refilling of the system. So this is we are sending water at a flow rate of around 10 milliliter per minute. And we could also observe one more interesting fact is the pathway of oxygen stays constant throughout the supply of current, so until the process is stopped. So this is one of the most interesting findings that we had doing in our group. But since it's a more homogeneous network and there are a lot of artifacts in the cell, so this is actually a prototype. So we are more working towards making into a smaller microfluidic and making this anodic porous transport into a more complicated irregular network structure. So to know more about our studies, you could also look into our publications. So the first 3 publication deals with our Pore network models, and the 4th one is the introduction to the Lattice Boltzmann model, and the 5th one deals with the macroscopic model and what are the aspects that we are looking in the macroscopic model. So here are the details about my colleagues and myself. So if you have any doubts, or if you want any interesting topics or ideas, we are ready to discuss in our group. So here is our contact details. So you could email us anytime you want. So thank you for your attention. And now I open the table for questions. Thank you.
Okay, thank you for your presentation. But of course, what you shown about LBM and Pore network simulation is also, let's say, an extension of what was done in the group of Evangelos Sass, but also in the field of drying. Here, of course, it's specific.
Drying, yes.
let's say, application, but it's also about mass transfer. So it can also, let's say, be applied in, let's say, the drying field. And I was specifically thinking to soil sciences, for example, because we have some collaboration with some colleagues from the agronomy faculty, and they are very interested in, let's say, wetting and drying cycles in the soils, also in link with climate change. And I had a question regarding, let's say, the current development of your models. Your networks are always considered as rigid, or is it possible to take into account, let's say, some, let's say, a change of the network, some shrinkage, or it's just a fixed, let's say, a volume?
It's fixed. It's fixed network. No, we don't consider the shrinkage.
Okay, but of course, in your application, it makes sense. But do you think that for, let's say, a more advanced application, it would be possible to take into account a change in the position of the size of the pores and so on?
Yes, yeah.
Okay, and just for my information, all these works that you do in collaboration with Magdeburg University, is it in the framework of a European project, or is it completely funded by the Max Planck Institute?
It's under the IMPRS PhD program that we work under the Max Planck Institute.
Okay. So I don't know if there are some other questions from the audience. Apparently not. So thank you for, say, sharing your work, and so hope to have some, let's say, more news in the future, because there are, of course, a lot of works done throughout, let's say, the scientific communities about, of course, production of hydrogens from water and so on. So there are a lot of, let's say, it's a tremendous field of research.
For the reason people want to focus more about the clean energy.
Okay. Thank you.
Thank you.
So we are, let's say, 3 minutes in advance for the end of the program. So I think it was it's a nice insight into some drying research in 3 different, let's say, European countries with quite, let's say, international profile. So thank you to the 3 speakers of this day, also for the kind introduction from the EFCE, but also, of course, concerning all operational and organizational aspects to Martin. So as we said, we opened this series of webinars today. I also, let's say, just make a small reminder for the people or participants who joined perhaps a little after the beginning of this webinars, that in, let's say, next year in July, we will go back for, let's say, a live conference about drying. So the next European drying conference will take place in Poland. So I hope that you will have the opportunity to join and to, let's say, to answer to the call of abstract that will be launched very soon. So at the end of this month, of next month. And also, as I said, if some of you are interested to join the drying working party, don't hesitate to write us an email. So thank you. And I, let's say, hope that you will have a nice and sunny week, and perhaps that you will have the opportunity to join to other webinars, because let's say we are interested in lots of other topics in the field of chemical engineering, let's say broadly. So yes, I think that I will stop there. So thank you so much, and don't hesitate to share and to disseminate, let's say, the link towards the recording of these webinars. So thank you to all of you. Bye-bye.